Okay, so
I try to keep it short. So thanks, Mircea, and thanks, Corina, for inviting me. Is everything set up? Oh, okay. So thanks for inviting me to give a talk here, and thanks to all of you for staying here and for voting to have the talk now. I'll try to keep the technicalities to a minimum. There will be some technical stuff, but I will start with easy pictures. The topic is also a bit unrelated to point configurations, but I will try to make the connections to some of the things that we've already heard during the talks. So it's going to be about the magnetization ripple, and I will show you some pictures in a moment. And the mathematics behind that, something we worked out with Ignat from Toulouse, Felix Otto from Leipzig, from the Max Institute, and Pablos Tsatsoulis from Bielefeld. So brief overview. What I want to show you is how to use interesting mathematics to address the universal character. Let me maybe move away a second. The universal character of a material science phenomenon, which you can actually see in experiments. How to model it probabilistically, and there we will see a kind of randomness that is different from the one that Franz Merkel talked about. So for him, thermal fluctuations were important. For us, it's going to be quench disorder that plays a major role. And I will also show you an interesting approximation, non-Gaussian approximation that we need of white noise. The problem is variational, and most importantly, what we try to do is minimize a non-convex energy functional that actually turns out to be in need of a renormalization procedure. The randomness somehow conspires in a bad way with the variational problem, so that the Euler-Lagrange equation actually turns out to be a singular stochastic PDE. So we'll tell you a little bit about the way of treating such a singular SPDE, and I'll also connect a bit from the way the energy looks like to some aspects of fluid mechanics. But I will try to keep it in a sort of soft fashion, and want to show you some of the ingredients, how to establish the universality of this material science phenomenon. So let me start by a brief overview of where we're actually located in. The whole thing is a phenomenon in thin film ferromagnets, and the theoretical description of magnetization processes on micron scale is typically done by the Landau-Lifshitz model, which is an effective mesoscopic model. And somehow in contrast to describing single spins, taking into account some of the quantum mechanical nature, we don't really see the magnetic spins, but model our magnetization just by unit length vector field on our magnetic material. And nevertheless, it's somehow a remarkably powerful theory that is formulated in terms of a relatively simple energy functional. Namely, it basically consists of 4 competing energy terms. The first one being the exchange energy, which somehow keeps this quantum mechanical character in mind and penalizes variations of the magnetization vector. The second one, and this one will turn out to be quite important for us, is the anisotropy, which tells you that the magnetization might favor a certain direction, the so-called easy axis E. And then also a magnetization by Maxwell's equations generates a field, the so-called stray field, which comes with its energy. And we might be sitting in an external field, which also produces an energy. Now, notice that the variational problem, since we're really interested in somehow once everything settled down in the saturation magnetization, we can always normalize it, and I will set it to 1 modulus 1 in my material and continue it with 0 outside. But that produces a non-convexity in the variation problem. And since we have this stray field energy, and the field is given by a solution of Maxwell's equations in the just static situation, we have a non-locality appearing. And actually, if you look at the Maxwell's equations, you can actually somehow solve the equations and write the stray field energy somehow as this inverse derivative of the L2 norm of the inverse derivative of the divergence of M. So as a sort of H-1 homogeneous H-1 norm. To understand this induced field a bit better, it's a good idea to write the stray field as the negative gradient of a potential, and that potential reveals some nice analogy to an electrostatic thinking, because since we are really interested in a finite material, we both have, if you look back to the Maxwell equations, this is satisfied distributionally in R3, so we have some interior terms, so the divergence of H is related to the divergence of M, but then we also might have boundary jumps because we have a magnetization that jumps from something to 0 on the boundary of the material. So the normal component of the magnetization actually produces something that you can think of as boundary surface charges, whereas you also have some volume charges, divergence of M, which produces a field in the inside. The combination of these 4 energy terms can lead to very interesting complex phenomena, and I would have liked to present something on domain branching, which would have been a bit more in the direction of the school here. That's actually an ongoing project with Felix Otto and Carlos Roman from the Católica in Santiago, but we're not really there yet to present the results. We've made some nice progress, but it's not finished, so I didn't want to talk about preliminary stuff. So let me focus on another phenomenon, which is the magnetization ripple. And you can even see it. Here's a transmission electron micrograph picture of a certain magnetization pattern, which is the cross-tie wall here. And on this cross-tie wall, you see that in the color code that there's sort of an oscillation, a fine oscillation of the magnetization, and that is the topic of today's talk. That's the magnetization. Now, how can we describe this magnetization ripple? So first of all, it is a microstructure formed in thin film ferromagnets, and let me show you another picture. It somehow has this nice property that it's always somehow an oscillation orthogonal to the average magnetization direction. So in such pictures, you can actually read off the main magnetization direction by looking at these fine oscillations, and the main magnetization direction is orthogonal to these oscillations. And the whole thing is triggered by the polycrystallinity of the sample. So you can really think of your thin ferromagnet as being made out of small grains, and each grain carries through the form structure of the grain a preferred axis. So it carries its own easy axis. So and in order to somehow model this stochastically, because we don't really know the process of manufacturing of this thin film, let's just assume we throw in some random IRD, random or Poisson point process on the plane to a Voronoi tessellation, and then throw in each of the cells a random vector, which somehow describes the easy axis in this cell. And what I want to work out and show you how to do that is a universal character of the phenomenon that this polycrystallinity leads to, namely these fine oscillations, the magnetization ripple. Namely that the ripple doesn't really depend on the precise structure of your grains, so the precise composition or geometry of the polycrystalline material, but really essentially just on one parameter, which I will show you next. So that's the goal. And now, of course, the model, if you look at all the 4 energy terms, that's far too complicated. So we have to make some model reductions, and that can be actually done in the regime where the grain size, the typical grain size of your polycrystalline material is much, much smaller than the typical length scale of the ripple. And that could be written down in some material parameters, but let me go directly to the energy that I want to study. can be essentially captured by the following total energy, which is an energy of the transversal magnetization component. So really think of your magnetization to point into the direction that is given by some external field. Say, let me fix that to be the one direction in the plane. Everything is a thin film situation, so let me squeeze everything to the plane. And we have one direction, which is given by the main magnetization from an outside magnetic field. And then we study the fine oscillation orthogonal to it, which is the M2 component, the transversal component, which I want to call U, to not always carry around the M2. Then what survives effectively of the exchange energy is a d1U squared. So variations in the one direction are still somehow suppressed by this energy here, harmonic energy in one direction. Then due to going to a thin film limit and working out Maxwell's equations, looking at oscillations around 1, the non-local stray field energy can be written as somehow negative fractional derivative in the one direction of this combination, which basically comes from expanding the square root. Remember that the magnetization was a unit vector, so m1 squared plus m2 squared has to be 1, which means if m1 is 1 and we just look at small oscillations, we can expand the square root of 1 minus m2 squared, and essentially reach at this energy. And then effectively the anisotropy energy, that can be shown to basically act like a field on the M2 component, so a field on the U, where the field is given by essentially by the random field I showed you in the sketch here. And if you zoom out, so in the relevant length scales, the field can be modeled by a white noise field. So that is the energy that I want to talk about. And the random field here really is a noise of quenched character, reflecting the fact that your material consists out of these small randomly oriented grains. Due to the stray field energy, I mean, there's nothing wrong in assuming that the noise is isotropic, but what one sees is due to the non-local stray field energy, this actually produces some anisotropy. So this leads to an anisotropic response of the magnetization, which has some implications in how we treat it, but let me not go into too many details here, but rather formulate the universality. But first of all, let's think about what one would do now when trying to study minimizers. So we want to study minimizers of this functional. Well, the first thing one could do is to write down an Euler-Lagrange equation. If you write down the Euler-Lagrange equation, it has some linear part, which is given by an elliptic operator, which happens to be non-local because of this negative derivative, but it is a second-order elliptic operator. Then there are some nonlinear terms, and the right-hand side, which is projected white noise. Well, where does the projection come in? You see that in order to have the stray field energy here finite, you have to, this inverse fraction derivative has to make sense, and that is only the case if you have vanishing average in the x1 direction. So you somehow can project out, project down to fields or to functions u which are of vanishing average in the x1 direction. So that's the key here. And then what you realize is that, okay, let's think of the situation that one can actually show that the equation is subcritical in the sense that at small scales, the behavior is essentially the one that you would expect from the linear equation. So let's look a bit at what would happen if we forget all these terms here. Well, then we would have something like second order elliptic operator on U is given by this rough right-hand side, given by white noise essentially. Well, white noise in 2 dimensions is a distribution. It's actually a distribution valued field, And due to our anisotropy, the counting of regularity is a bit different. So it turns out to be a distribution which, measured in some negative Hilbert spaces, is of order minus 5/4. Oh, sorry, it's 5/4. Yes. So now, if you look at this operator here, it improves regularity by 2. But then if you look at this term here, you can work out what this term is. Then you see that essentially what you're trying to do is multiply an object which is of negative regularity by something that is of positive regularity, but not enough regularity to make sense of this product. So that's why this Euler-Lagrange equation is a singular stochastic PDE, but using some of the standard theory, using a renormalization procedure, which is here in this case just micro-renormalization, you can do a somehow small noise theory by means of a fixed point argument. What I want to show you is that the smallness of the noise is actually not needed. We want to study the existence of an arbitrary parameter in front of the noise. And for this, it's better to work directly from a variational point of view. And the variation is also really looking at the energy instead of the equation also makes sense, because we cannot really expect uniqueness of the minimizer because the variational problem is highly nonconvex. So I really want to work at the level of the energy and express universality on the level of the energy. But then we have some problems. And the first problem is that the energy isn't bounded from below. One can actually show that if you take the solution of the linear equation, so Lu is sigma peak psi, that if you insert this solution, then almost surely under the law of white noise, you get minus infinity as an energy. So at this point, as someone from calculus operations, you might say, okay, good, then I can go home. But it's not so bad. It's not so bad because that's essentially the only infinity that happens. So by subtracting this minus infinity, one actually ends up with an object that that has chances to be well defined. We can actually split this difference here into sort of an anharmonic part, which has this nice Berger's nonlinearity here, which came from expanding the square root, which I briefly explained. And this is actually one of the difficulties when working in a somehow variational framework, trying to establish good properties of E, but let me not dwell on that, and some remainder G. Now, the remainder G still has a problem because by the same reason why the equation didn't make sense, this product here turns out to be ill-defined. So we have to do a bit more. We have to work a bit harder, but by imposing some sort of renormalization rule, and that makes a connection to this lifting procedure that we've already seen, I can actually impose a rule and say, okay, this guy here is some distribution with somehow the worst regularity of these two terms, which turns out to be minus 3/4 minus, but that's not too important here. So I replace this object here by something else, thereby somehow lifting the problem from noise to noise and this renormalized object. And in a Gaussian setting, you can actually write down what this is. This is somehow a limit when you smooth out your white noise, so I say a smooth kernel, and take the limit, which turns out to exist by some stochastic estimates. Now, if you have in mind the model that I showed you before, so random grains with random easy axis, and this is far from being Gaussian. So somehow in trying to understand the physics of the model a bit better and essentially establishing a universality result, it's not a good idea to restrict ourselves to Gaussian noises. And that's where technically sort of the spectral gap inequality comes in. So the kind of noise and the kind of class thereby in which our result holds of random models for the spring orientations is the following. So we have centered noise, which is stationary and has some invariance property, which leads to the fact that some ugly terms, so that some renormalization constants in the end disappear by symmetry. But most importantly, it should satisfy a spectral gap or infinite dimensional Poincaré inequality, namely that you can somehow of suitably nice nonlinear functions of your noise, you can control noise minus its average in a stochastic L2 sense by the L2 norm of the Meyer-Bar derivative. Once you have this, you can actually show that you have an LP version, and that somehow gets you going, because that gives you somehow a replacement for Gaussian calculus in the sense that you can control higher stochastic moments by L2 stochastic moments, so by the variance. A good thing is in this class of noises that I want to consider, white noise is actually contained. And immediately that spectral gap inequality gives you some a priori regularity, namely the spectral gap implies that these measures here are actually not really measures on Schwarz distributions, but they are somehow concentrated on a much smaller set, namely they're supported on distributions which have some -5/4 minus epsilon Hölder regularity. So if you're not really comfortable with this Hölder scale, maybe you've heard of Besov scales. So that's somehow the natural scale in that problem. Now, once we have that, so we renormalize the energy, we renormalize this ill-defined product, we can look at this somehow doubly renormalized energy on the natural set, namely on the set with the quadratic form of the linear parts of the harmonic part of the potential of the energy is finite. And what I want to show you on the next slide is that using the topology of gamma convergence, which is the right topology if you want to study limits of minimizers of approximating functionals, and really have in mind we're somehow approximating by convolving or with a smooth kernel, convolving our noise with a smooth kernel, or approximating our noise by these nice probability measures. So using the topology of gamma convergence, we can give a sense to the laws of the distribution of this renormalized energy in such a way that it is independent of how we approximate white noise in that class. And that is really the universality that we were aiming for. And that's somehow the technical statement. So given a probability measure that satisfies the properties I just showed you, we can extend it to a probability measure on noises and functionals. So noises and energies, if you like, such that if you take the marginal, so the law of Xi under this extended measure is just the measure you started with. If it's smooth, you have exactly what you would expect, namely then every product is well defined, and you agree with the guy you get when you just write down what you would naively want to do. And most importantly, we have a continuity, namely if you approximate some limiting measure, think of white noise, then the extended measure converges to the extension of the limit measure, namely to the extension of white noise measure. So that really gives us a way, even though we cannot really work with the sort of energy functional for the law of white noise, so really working with this irregular white noise, we have a way of approximating it in a continuous way to make sense of its law in this extended space. And that as a corollary easily gives us the almost every existence of minimizers, and that you can think of as the magnetization ripple. And for any P, we somehow have the right regularity estimate, but that's something we want to skip and just show you on one slide what the main idea is. So the main idea is really this lifting, and that is an analogy to rough paths or regularity structures, so Alliance, Rubinelli, and higher, namely that in a first purely probabilistic step, we construct somehow in a consistent way this renormalized product and lift our problem to the space of Xi. So okay, B is just somehow given uniquely by Xi, and this additional renormalized product, and that can be done by some stochastic, on an offline stochastic step, which depends mostly on the spectral gap inequality. And then deterministically working on that space, we can derive a continuity with respect to gamma convergence of the map that takes such a triple and maps it to X's and renormalized energies. And that is really formulated in the sense of continuity with respect to gamma convergence. So we really get convergence of minimizers as an easy corollary. And in that way, you can think of lifting the problem to this tuple of noises and functionals, which is consistent if the noise is smooth. And that's everything I wanted to tell you. I know it was very fast. If you want to see some details or if you want to understand some details more, I'm here till tomorrow evening, so feel free to approach me. Let me just conclude that I showed you somehow very sketchily the universality of the magnetization ripple, which is a well-established material science phenomenon, which is triggered by this quenched noise, so by this random grain orientation. And what we used here was somehow gamma convergence techniques in combination with a rough path type strategy, which, as far as I know, is one of the first times that these ideas have really been used in a calculus variations approach, in particular in a non-perturbative approach to solve such problems which relate by its Euler-Lagrange equation to a singular SPDE. In the background, there's some spectral gap inequality to take care of the non-Gaussianity of the noise, which somehow is naturally in the problem setting. And deterministically, of course, you also have to work a bit. That I somehow did. Since the Burgers operator is not immediately seen to have nice coercivity properties, but actually has to work a bit to tickle out of this expression, especially this negative half derivative, to tickle out some coercivity properties that you can control some of the nonlinear terms. And this is done with a nice fluid mechanics identity, which in principle tells you it's a very easy but not really directly apparent identity for the Burgers operator, which shows you that you can actually control half a derivative in L3, and then that gets you going, and then of course you have to work, but it turns out to be just the right thing, and some Schauder theory for nonlocal equations to get the gamma convergence. And with that, let me stop. Thanks for bearing with me, and yeah, if you have questions, whenever you like.
Any questions? Yeah, interesting talk. I missed some basic points, I think. So the randomness comes from a random grains in the material, so that gives you a random easy axis.
Exactly.
So this E dot M, whatever term in the
exactly.
micromagnetics that tells you that so physically that the magnetization aligns with some kind of crystal lattice structure. So this would work for particular crystals, yeah, let's say tetragonal or something like this. Okay, so but then this term in the overall function, it's not the leading order term in terms of derivatives. So you have the exchange energy, which is kind of yeah, in the Euler-Lagrange equation, you should get a Laplacian from that. So
exactly.
Then what I didn't understand is why there's this strong singularity. So it looks to me like we should have an equation with a deterministic Laplacian coming from the exchange energy, because that's always there, regardless of how the crystal is oriented, spins onto a line. So that's the exchange. And so then the randomness is kind of in a lower order term. So therefore, I did not understand why your stochastic PDE is so horribly singular that you have to go into, I mean, God knows what, all this Martin-Heira stuff, very admirable, but best avoided that you do it at home.
Yes, so we actually don't have to go through all the Martin-Heira stuff. So it turns out that we can do a very basic, essentially Victor normalization. So that turns out to be enough. But you're right. I mean, it's not really.
Why is this SPDE so singular? That's what I don't understand. I see a nice Laplacian, and then at the lower order term, I see a random coefficient.
Okay. So that also has to do with the way how we treat the equation, and what we do is, I mean, it turns out that due to this thin film limit, you somehow get this negative half derivative of this Burgers term. So there's, I mean, essentially what we're studying is really small oscillations around the 1-0 magnetization.
So is it because of the same film limit that becomes singular?
So that gives us an anisotropy that we see in the equation, in the sense that, okay, it's a non-local operator, but the operator somehow has an anisotropic scaling. It treats the D1 and the D2 direction somewhat differently. Now, if we equip our space.
Okay, so if you didn't have that, you would still have a Laplacian somehow.
Then we would have a Laplacian,
and then it would not be a singular.
And then this term would not be singular.
Okay, very good. Okay, so it came from the thin film limit.
Exactly.
So
Yeah.
Okay, I think now I understand. Okay.
So then essentially what you do is you somehow work in a space which respects the scaling, so the D2 derivative actually has to be scaled differently than the D1.
So can I put it back very vaguely? So roughly speaking, when you are in the thin film and spatially far apart, there's not enough elliptic communication between the magnetizations anymore to align them nicely. And there would only be, after rescaling onto a fixed domain, there's enough elliptic communication between spins that sit, underneath each other in the thin film, but not far away, because then the interaction is mediated by the thin film, and then the use the kind of
yes. So I think that's a fair way of saying it. Okay. I mean, what I somehow hear is that we are anyway making another brutal approximation by putting everything on the torus. So white noise anyway only triggers small oscillations or small scale oscillations, and that is why we, in the first approximation, someone say, okay, let's go to the torus. We would like to study the whole thing in the limit when the torus goes to infinity, but then there are some other problems.
That I understood.
Yeah.
But that has nothing to do with this.
Yeah, exactly. Right. Yeah.
Okay. Maybe we can keep interacting with Tobias in the following hours, the next days. And meanwhile, let's finish the sessions of today. And